There we go. Hello, hello. This is going to be the calculations video for the bonding and metal chelation experiment. So the lab data you have uploaded should be something similar to this. It should have a picture of the titration and some data. There's usually also an example line. The calculations are typed through for that document, or you can also watch this video where I'll be going through all of those step by step as well. So the top table we have is all of the measured values, the volume of iron solution that we measured out, the initial and final volumes in the burette. The volume delivered technically is a calculation. I will show it really quickly. So it is literally just the final volume minus the initial volume. .3, and that's all that is. Again, check sig figs. We're doing subtraction, so we care about the number of decimal places. This has 2 decimal points. This also has 2 decimal points. So our answer should have 2 decimal points, and it does. So all of that, that's the easy calculation. Oop, that moves with it. So that's how we got the volume delivered. The molarity of EDTA was provided on the bottle. So to fill in the table that we really care about, where we're getting all of our calculated values, molarity of EDTA is just copied from above. Not that one, that one. And it was 0.100. And so that was the same for all 3 trials. So we can go ahead and copy those down. Volume delivered of EDTA was that value we just found up above. So the first trial, 4.13. Second trial, it was 3.24. and 3.72. So now we get into the real calculations. So I'm gonna make this a little smaller. Oop, too small. There we go. Okay, so now we get into the real calculations, doing some of the stoichiometric calculations. So to get to moles of EDTA, if you're going to use the little diagram mentioned in the stoichiometry experiment, I'm not going to write in everything. I'll just use the shapes. So we have a volume. We're trying to get to moles. And so all we have to do is use the molarity and go down this line. So to set that up as dimensional analysis, start with our 4.13 milliliters of EDTA. Because we want milliliters of EDTA to cancel, that means it needs to go on the bottom. And as we remember, molarity is in moles per liter. So the first thing we'll need to do is convert this to liters of EDTA. Gets rid of that. Now, liters of EDTA is not what we wanted to end with, so we need to get rid of it. And what can we turn liters into? Well, our diagram says we can go from liters to moles using the molarity. So we can convert that into moles of EDTA. And then we just have to figure out the values. Well, the molarity provided to us, that number goes with moles, so 0.100, and then the liters gets a 1. Liters of EDTA cancels out. We're just left with moles of EDTA, which is what we wanted. So 4.13 times 1 times 0.1 divided by 1,000 will give us, let's see, 0.000413 moles of EDTA. Now, we should always check our significant figures. We're doing multiplication and division, so we care about the number of significant figures. Our volume has 3 significant figures. This is a metric conversion, so it has infinite significant figures. Our molarity has 3 significant figures, so we need to round our answer to 3 significant figures. These are leading zeros that don't count. We have 3 significant figures, so we don't need to change anything. So we can now put this answer in. And I was going to do scientific notation. I can't make it do it the way I want, this way. So 0.000413 moles. Okay, so we can do the same calculations for the other 2 trials. Let's see, so this number will change. We'll still be in milliliters, have to convert to liters. Actually, let's just erase all of it. You can do the same thing with the next one. 3.24 milliliters of EDTA is what we start with. We want to get rid of milliliters of EDTA. Again, notice how I'm using both a number, a unit, and a label. Again, when you're talking about stoichiometric calculations, and at this point in the semester, you're really going to be dealing with lots of different chemicals. So you want to make sure you know definitively which chemical each of these numbers is associated with. So I set it up the same way. Just looking at the units, we want milliliters of EDTA to cancel, so it needs to go on the bottom. We can convert that to liters, but we wanted to end with moles, so we need to do another conversion so that those cancel out, and we're left with moles of EDTA. Now if we go back and fill in our numbers, liters, milliliters, this is a metric conversion. Anytime we see moles and liters, that's a molarity, and so we just have to go find that molarity either in the question or on the bottle given to us, something to that effect. We do the math, and we get 0.000324 moles of EDTA. Again, if we check our significant figures, this has 3, this has infinite, this has 3. Our answer should and does have 3. Okay, we could do the same calculations with our last trial. And the only thing that's going to change is our volume. So the rest of that will stay the same. So I'll go ahead and leave it for now. Now we have 3.72. We do all of that math and we'll get 0.000372 moles of EDTA, which again also has 3 significant figures to match our measured values. Yeah. So that's how we get all of those values. To get the moles of iron 2 in our solution, we go back to our little diagram. We can do this one of two ways. We can either start from the moles of EDTA that we have, or we can start from the volume that we were originally told. We need to get to moles of iron, which is a different chemical. So we'll need the molarity of EDTA and the molar coefficients between EDTA and iron. So if you look back in some of the pre-lab material, I believe it's in the slides as well, you'll see the equation. The iron 2 ion reacts with the fully deprotonated EDTA. Again, we want to do complete chelation. So we need it fully deprotonated to give us this iron EDTA complex. And this is not one of your normal reactions, so I would not expect you guys to be able to generate this. This is why I provided it to you. But if you look, all of the coefficients are 1-to-1. We have no numbers written, so we assume they're all 1-to-1. And that means we can, for the first one, I'll start all the way back from the volume of EDTA. So just looking at units, we want milliliters of EDTA to cancel. So we need milliliters of EDTA on the bottom. We can turn that into liters, which we will need for the molarity. Because our first step is using the molarity, but that's moles and liters. So we'll need to deal with that. For now, I'm not going to fill in numbers. I'm just going to deal with units. We'll go back and fill in numbers. But liters of EDTA isn't what we wanted to end with. We want moles of iron. So we need that to cancel. And now we can convert to moles of EDTA. But again, moles of EDTA isn't what we wanted to end with, so we need another conversion factor. And now we can use our coefficients to get the moles of that iron ion. Now the units we're left with is moles of iron 2, which is what we wanted. So now we just have to go back and fill in numbers. Liters and milliliters, this is a metric conversion. Hopefully you guys have those down by now. Moles and liters is always a molarity. The number goes with the moles. The liters gets a 1. Moles and moles is coefficients from a balanced chemical equation. We have nothing written in front of the iron, so that means it's a 1. We have nothing written in front of EDTA, so it's also a 1. So we do this math, and we'll get 0.000413 moles of iron. And again, this is exactly why I say to add a chemical label to these, is if you didn't, you end up with lots and lots of moles, and it's hard to remember which mole went to which thing. So we can do that, and I'll fill that number in a minute. We can also shorten this up a little bit if we just start from the moles of EDTA that we found. So for that next trial, (0.000324 moles of EDTA. We can go from moles of EDTA to moles of iron. and it's still a 1-to-1 ratio. So we'll get 0.00324 moles of iron 2. So we'll go ahead and fill all of these in. If we had rounded our moles of EDTA, you would make sure you want to go back and use that full number. Again, you don't want to round a number and then round it again and again and again, because you get further and further away from your true value. But since we didn't, we can just use that value as is. You can always go back and not have to worry about using the full number. If you did round, but you accidentally deleted it from your calculator, didn't write the full number down, you can always go back to the original, in this case, the volume, and do the calculation all the way through and check your significant figures. So because this had 3, this has infinite, this has 3, again, coefficients, we don't count their significant figures. So we need 3, which this one has. Again, because we didn't have to round anything, just starting from here is fine as well. And that's why I went ahead and already did the last one as well, since it's 1-to-1. This time, we end up with the same number of moles of iron in EDTA, but that's only because it's a 1-to-1 ratio. If this was a 1-to-2 or 2-to-1 or 3-to-2 or any other value, these numbers would be different. Let's clear all of that. And that one. There we go. Volume of the iron solution was a value we reported up above. It's one of our measured values. So I'm just going to copy those down. 38.7, 49.1, and 48.8. There we go. So now we need the molarity of our iron solution. Again, 2 different ways to do it. I'll do the longer way first. These data tables were specifically built so that they walk you through each of these step by step, but you could just go from beginning to end. You could just start with the volume of EDTA delivered and go straight through to the molarity of your iron solution without stopping at each of these points. Again, these data tables were set up so that it would help walk you through them. So if we start with volume of EDTA, we want to get the molarity of the iron solution. So we want to find this. That means we'll need the volume, which is what we just copied down, and we'll need the moles of iron. So to do those calculations, we'll go from volume of EDTA to moles of EDTA, moles of EDTA to moles of iron, and then we'll just use the volume of iron to make it all work out. So again, long way first, starting all the way back at the milliliters of EDTA. Get the milliliters to cancel, get the liters of EDTA to turn into moles of EDTA. Moles of EDTA into moles of iron. And then we need the volume in liters of iron. And because molarity is moles over liters, and we have moles on top, we'll need liters of iron on the bottom. So we end up with moles of iron 2 over liters of iron 2, which is the molarity of iron in this case. Again, this has to be the liters of iron, not the liters of EDTA, because they're different chemicals. Let's fill in our numbers, metric conversion, Molarity, it's the same molarity we've been using. So 1. From our coefficients, those are both 1 to 1. And we have the volume here in milliliters. So to go ahead and convert that into liters, I'll do that for 7 liters. It's supposed to be right there. So if we do that math, 4, 7, we get 0.00848044928 moles of iron over liters of iron. So this definitely has more significant figures than we're allowed to have. All of our measured values have 3 significant figures. Everything else is a metric conversion or a coefficient that has infinite significant figures. So this needs to have 3. Leading zeros don't count. 1, 2, 3. We'll round after this 8 and get 0.00848 molar iron 2. Okay, so let's go ahead and plug that in. There we go. So again, because all of these numbers have been working out so nicely, because we've set them up to step you through this one step at a time, we can shorten this. Let me just clear all. From the moles of iron that we found. And we can just divide that by the volume of iron that we had. Again, this time I'm using the milliliters just to show the conversion, but you do need that value in liters before you can complete your calculation. So I'm just showing that conversion here. I did it in my head last time. Since I have the room, I went ahead and showed it. And we get 0.006598778 molar iron 2. Again, still need 3 significant figures. Leading zeros don't count. 1, 2, 3. We're going to round here. This is going to round up. That's a 9, so the rounding gets a little strange, but nothing too bad. 660 molar iron 2. And that's what we'll go ahead and put into data table. And then we'll do the same calculation for our last trial. Again, I went ahead and did this conversion in my head. We have moles over liters. And we get 0. And as I've mentioned before, I always like writing out the whole number that the calculator gives me. That way, if I was doing this on paper, I would have a record of it. So if I needed to go back and check my significant figures or use a longer number, I can. And it helps me show exactly where I'm rounding and know what I'm doing. So this becomes 0.00762 molar. Cool. The average molarity of iron should be a fairly straightforward calculation. You add up all of the values you have. And then divide by the number of values that you added, just like a normal mean or normal average. Even though it's not entirely necessary, I do still include the chemical labels. It's a good habit to get yourself into. Ideally, I would use the full numbers from when I did these calculations originally, but unfortunately, because of the annotation method on Zoom, those are deleted. So this should be close enough. But if you have those numbers, when you guys do the calculations, I would use the longer number, not the rounded numbers I have here. So we're doing the addition. So all of these have 5 decimal places. We don't care about the significant figures from this 3. It's an exact value, so we don't worry about it. So basically the numbers that we plugged into it should be the same what we have here. So 1, 2, 3, 4, 5 decimal places, and we'll get 0.00757 molar. Go. So that's all of the calculations for this experiment. One of the post-lab questions will have you calculate the accuracy of your molarity. So I don't remember the exact number, but I'll make one up. Let's say it's supposed to be zero, 1. Let's say the stockroom told us that it's actually 0.01000 molar. So we can get our percent error. Which is the absolute value of actual minus theoretical over theoretical times 100. So this is our actual value. This is our theoretical value. So we can just plug that in. I am going to drop the iron label for now, just because I'm running out of room. But I am still going to keep the units because those are important. So if we do this top difference, you will get a negative number, but that's the point of the absolute value bars, is it ignores, oops, it lets you ignore the negative sign. That way none of your percent errors will ever be negative. So we do all of that math and we get 24.3. And we can base our answer off of the number we plugged in. If you track it all the way through, it ends up being decimal points for this difference and then 3 significant figures versus 5 significant figures. And so our answer should have 3 significant figures, which in this case it does. And so we don't need to do any rounding. So that's not a great percent error, but I also just kind of pulled the 0.10 out of thin air just so I could show you the calculation. But that's how you do it. For the percent error, your average molarity that you calculate is your actual value. And then the one that the question provides you is your theoretical value that you plug in for those spots. So that is absolutely all of the calculations you should have to do for the bonding and metal chelation experiment. So hopefully this answers all of your questions. Again, it's typed through in the lab data that's uploaded. If that still doesn't work, reach out to me and we will we'll work it out and everything will be just fine. Thanks, guys.